Recording. All right. Yeah. So to start off today, I will be talking about my personal favorite event, which is Dynamic Planet. And specifically, I'll be talking about oceanography, which was the topic when I was in SciLE. So let's jump straight into it. So this is the event rotation that's been here for perhaps the past 1 or 2 decades. So yeah, as you see in like the 2021 to 2020 years, it was oceanography. For the past 2 years, it's been Earth's freshwater. So I'm expecting this to change next year, but maybe to glaciers, maybe to tectonics, something else. But yeah, Dynamic Planet is your standard Earth science event. Really fun. So to start off with oceanography, I don't see a better starting place than seawater. So let's talk a bit about it. So seawater is 3.5% salt, and this is something that's tested quite heavily. Then it's something that you definitely should put in your binder. So 3.5%, also 35 parts per thousand. On the top right here, I've shown kind of a distribution of the salts. So obviously seawater has salt, so NaCl occupy a large quantity of the ions, but there's still others like maybe sulfate or magnesium or calcium and potassium. And you should note potassium is an element. It has a charge of 1 plus, and all you need to know is that that makes potassium rather reactive. And yes, it is in bananas. Yeah, so for components of seawater, know these 6 ions and you'll be fine. Additionally, salinity is surprisingly highest at the mid-latitudes. And this is because if you're at the poles, then you have too little evaporation, and so there's a lot of water. But in the tropics, there's too much precipitation, which also allows water to go into the ocean. And so that dilutes the salt and makes it less saline. So one more thing you should know about salt water is that it melts at, it boils at, well, again, sorry, no, it freezes at -2 degrees Celsius, and that's 28.4 degrees Fahrenheit, which is slightly lower than normal water, I guess pure water, because the salt holds the water molecules together and then makes it liquid and makes it harder for the water to freeze. All right, water and heat. Now, water has 2 other important properties that make it really important to the Earth's ecosystems. And that's that it has a very high heat capacity and also has a very high latent heat of fusion or vaporization. And these are very complex terms that you might hear later in courses like AP Chem. But for now, all you need to know is that it means it's really hard for us to heat up water. And that's why, like, in the summer, it's a very popular activity to go swimming in the pool or swimming in the ocean, because while the land gets heated up quite quickly by the sun, then but the ocean would get heated up a lot slower. And that's why if you live in San Francisco, which is not quite far away from the Bay Area where I live, it's often very cool and foggy in the summer. Yes, Samuel, that is true. 100 degrees Fahrenheit is the boiling point. Additionally, the latent heat of fusion and vaporization makes it hard for water to change states of matter. So you need a lot of energy to boil water, but you also need a lot of energy to freeze water. And that's why ocean water is just almost always water, because it requires such an astronomically large amount of energy to either be given to water or taken away for all the oceans to freeze over. And so that makes ocean water practically liquid all of the time. All right, let's move to the zones of the ocean. So on the left here, I've depicted what's known as the thermocline. And once again, this is something that's tested quite often. Now, normal temperatures are between 20 and 30 degrees Celsius, and that's probably around the 60, 70, 80s Fahrenheit. And so the ocean surface, because it's warmed up so much by the sun, it's really warm, and it's about as warm. Okay, anyways, but we note that maybe around 500 to 1 kilometer deep, all of a sudden the temperature drops quite precipitously and almost to near freezing temperatures. And so this is something that's really important because that means most of the life is above this 1 kilometer depth. And so all the light doesn't penetrate beyond this point. And so most of the ocean is just so cool and almost freezing. Similar things happen with salinity, as like salinity would also rapidly increase as you increase with depth around this climb. Can you give us science Olympiad tips and tricks at the end? Yes, I actually have that planned. Yeah. All right. Moving on to different types of zone. On the right here, I have just a big diagram of oceanic divisions. And by the way, Dynamic Planet is a binder event. That means you have essentially infinite places to, or essentially infinite paper for you to put on down all of your notes. And thus, it's really important for you to load your binder with graphs, because this graph will convey so much more information than perhaps a paragraph even of this length could. And so it's really important. Picture is worth 1,000 words, and that's quite important. That holds quite well here as well. So in terms of depth, there's kind of like what I call the 5 pelagic zones. You have the epipelagic zone, which is also known as the photic zone, and this is where most of the light is. And then also, I guess, then as you go deeper and deeper, you get to the maybe mesopelagic, bathypelagic, piscopelagic, and hadopelagic zones. It's also helpful to know at which depths these zones kind of begin and end. Sometimes they're tested as well. Right. On to ocean topography, which kind of links hand in hand with the zones of the ocean. And so when we're going from continent to continent in an ocean, obviously this is a much reduced scale, but the general things to apply. So around the continent, it stays flat for a while, and then very suddenly you drop down, and the depth rapidly increases. And this is what's known as the continental shelf. Perhaps you've heard of it. Basically, it's kind of like when the slope of the slope underwater is really large, and so that kind of differentiates between where perhaps tectonically the continent is defined and then ocean is defined. And so once you go down to the continental slope, most of the time you'll reach what's known as the abyssal plain here, which is just big patch of flat, I guess, land underwater. Obviously, this is kind of like a condensed. This graph is condensed, so there's a lot of things. Most of the time, you'll see abyssal plains, and then the rest of these are just features. So let's go left to right. So perhaps you have a volcanic island arc, which is pretty self-explanatory. Volcanic islands, maybe they protrude above the water, maybe they don't, but they form kind of a barrier to the to the continents. You could also have abysses where the depth falls even further. Sometimes also trenches do the same thing. And then you get to the mid-ocean ridge, which is a really peculiar place. And this is where new rock is secreted from the bottom, or at least from under the crust, from the magma. And then this is also where seafloor spreading, if you've heard of it, occurs. So as the rock gets pushed up, it pushes the already there rock to either sides towards the continents. And so that's what happens. And then you get new rock, and then the ocean widens. So perhaps you've heard that the Atlantic Ocean is widening. And that's in part due to the mid-Atlantic ridge, which is the Atlantic's mid-ocean ridge, being really active and pushing rock to either side. Any questions? Hydrothermal events. Well, I guess there are hydrothermal events, obviously, but I guess they don't qualify to be as a feature, since sometimes they're just there. Yeah. Additionally, you should know what seamounts and guyots are. So seamounts are underwater mountains, I guess. Perhaps sometimes they're just one maybe there's multiple seamounts in one place. A guyot is a seamount which has a flat top, as you can see here. So yeah, ocean topography is tested quite a bit. What is a guyot? I just answered. How do each of these form? Good question. Some of these I don't exactly remember off the top of my head, I guess. Continental shelf is just kind of how continents like work as the land masses kind of like protrude above the ocean. The continental shelf forms. I guess for the mid-ocean ridge is just the magma, and yeah, it's also useful to know which of these form. Is there a difference between abysses and ocean trenches other than depth? Good question. I'm not quite sure. I would assume that a trench just goes much deeper and an abyss probably is not. How did the guyot's top get flat? My best guess is probably erosion, and eventually kind of like the top just crumbles and then it flattens out. I'm rather sure that seamounts and guyots have the same origin. Trench is just a lower trench. You're just like slit in the ground, maybe not like a dent. Good point. All right. Is the deepest ocean part the Mariana? You spelled it wrong, but yes, that is the deepest part of the ocean. Some you might need to know that sometimes they throw in what's the deepest part of the ocean in the Atlantic, and I actually don't remember. I think it's around Puerto Rico or somewhere, but yeah, I had to do some extra searching to tell you. Moving on to some tectonics when it comes to oceanography. So the most important thing you need to know is that dense oceanic crust will sink below the continental crust. And so this is because oceanic crust is kind of compressed, it's basaltic, and then the continental crust is kind of just floats kind of, I guess. And it's the same property with density. So the oceanic crust will subduct. That is, it will move under the continental crust. And then this will lead to, if we go back here, if we go back to the previous slide, sorry. If there's perhaps subduction going on here, that will pull the mid-ocean ridge out even more. It also gives the magma underneath here more rock. So this kind of leads to the formation of volcanic arcs. And there are a bunch of other features. And so, yeah. All right, types of reefs is important. So surprise, surprise, types of reefs were classified by Charles Darwin. And if you're like, hey, that's the guy who discovered evolution. Yes, it's the same guy who discovered evolution. Surprise. So basically, Darwin had a theory on how atolls form. And so his theory, as later it's proven correct, goes like this. So first you start off with an active volcano. And then after that, the volcano, after that, some reefs build around the volcano. And so this is what's known as a fringing reef. And this first picture here is a fringing reef. Basically, it's a reef that kind of just sticks around the shore, and it just kind of like envelops the coast. And then after the fringing reef forms, then the ocean, as the reef continues to build, the volcano kind of returns to the ocean, and so the rock gets eroded, and then the volcano starts to sink. And now this forms what's known as a barrier reef. It's the same type of reef as the Great Barrier Reef. It's shown in this a second image up here. And so it's, what I like to think of it is like it's a fringing reef that's like much bigger in every way. It's much bigger, it covers far more area, and it's also kind of just a better barrier. So an atoll is when a volcano is completely submerged in the ocean. Well, I think strictly defined, the atoll is the coral reef, but very similar. What is an atoll? I just described it. But yeah, atolls form when volcanoes kind of sink. That is what Darwin said. So, and in this third picture here, this is after what happens after a fully formed atoll. This is what a fully formed atoll looks like. Sometimes there are also like pieces of land around there. And so it basically becomes kind of this ring in the ocean. There are a lot of islands in the Pacific that are atolls. Who knows, maybe you've been to one, or maybe you'll go to one and hopefully you find it cool. When does the volcano stop erupting? Okay, this is not within the scope of oceanography, but it's volcanoes, basically they thrive off of the magma that builds underneath them, right? And so while there's magma, there's pressure, and so occasionally it erupts. But if for some reason the magma source is cut off, or the magma solidifies and loses all of its heat, then the volcano no longer becomes active and stops generating rock. Another question, is the volcano going to stay there forever? No, it will return to the ocean. It will, does the atoll stay there forever? Well, all coral reefs eventually kind of like die out. Corals are animals, by the way. I should totally mention that. So animal populations eventually will die out. I guess nothing is permanent. But yeah. Don't some volcanoes stay, like Big Island on Hawaii? Well, yeah. Erosion, I would assume, is a very long process. And so the Hawaii volcanoes are relatively, they have been relatively active within a time that geologically will be called very short. So yeah, are corals partially made of rocks? I believe so. I am not sure. And no, they are not plants.
Corals have calcium carbonate.
Yes, that's their shell. So I guess if you want to call calcium carbonate a rock, they are partially rock. But then that's kind of like saying we have metal inside of us. So, well, yes, they definitely do cling on rocks as well. All right, let's shift gears a bit and move into waves. And so waves, we must make one distinction first. So we need to classify kind of two types of waves. First are deep water waves, where the depth is greater than half of the wavelength. And I guess before I talk about this, who here has taken a physics class where they've talked about waves? All right, then perhaps it's useful for us to do a bit of wave review. I'll say some physics for Sound of Music. Oh my God, Sound of Music. Oh my God, Sally. Awesome. So yeah, waves, there are several important kind of like variables within a wave. And so this is what's known as a transverse wave. So all ocean waves are kind of like transverse waves. If I'm being really specific and nitty gritty, they're actually what are known as Rayleigh waves, but they're similar to transverse waves. So all the waves have kind of a median line, and then they go, sometimes they go above, sometimes they go below. And that's generally what it is. Yeah, this looks like a sound or light wave. That is true. Ocean waves don't actually look like this. I will explain lambda in a bit. So there are several important points. First is the crest. This is the topmost part of a wave. So it's kind of like the highest point, and maybe you've heard this term before. Trough is similar, but just reverse. It is the bottommost part of a wave, or the lowest point. A wavelength is the distance between two crests or two troughs. And now this is important. This is the lambda. This is the Greek letter lambda, and it corresponds to wavelength. And additionally, you should know amplitude, which is the distance between a crest and the median point. Now, there's another variable that isn't on here because it's kind of hard to describe. It's frequency. Okay, that was annoying. I'm sorry. Sorry, group chat is disabled. So another variable that I didn't mention is frequency, and this is kind of hard to characterize here, because frequency is defined as the number of wavelengths that pass within a certain amount of time. And so it's like if I start a timer when I'm here, and then 1 second later, this crest over here has moved all the way over here, then the frequency would be 2 hertz, or 2 1/2 second. So this will lead itself to a very important formula later on. What is amplitude? The amplitude is the distance between the crest and the median line. So deep water waves would have a depth that is greater than half of their wavelength, and shallow water waves would have depths less than 1/20th of their wavelength. Now, what's surprising is, and something important, is that tsunamis are all classified as shallow water waves. And you might think this is weird. Whoa, tsunamis are so tall. They're known for being abnormally tall and causing destructive with such high amplitude. But as it turns out, they have really massive wavelengths. And so this is why you don't see two tsunamis suddenly like come within a span of minutes or maybe even hours. And thank God that's not what happens, because otherwise we've been in a bit of trouble. So this means if they have a really long wavelength, then that means that between two tsunamis, there's a very large distance. And usually this distance would be greater than 1/20th of their depth, than 20 times their depth. So that would classify them as shallow water waves. To answer, are tsunamis classified as rogue waves? I guess they're classified as rogue waves, but they're not rogue in the sense that we know how they form, and we know they form differently than other types of waves. And so perhaps they're not like just suddenly surprisingly big. Don't waves slowly decrease as they progress? Well, what about a wave decreases? Is it the crest? Because that's not always true. If you have a hypothetically perfectly flat seafloor, then the crest would always be the same. But no. Is there in-between wave between wavelength over two, between shallow and deep water waves? Not that I know of, and I've never been tested on something like that. Does the second tsunami weaken before reaching land? I don't think there have been second tsunamis because that distance is just so large. Perhaps it does weaken before reaching land. Could an ocean have waves as big as a tsunami? Rogue waves? Maybe, but tsunamis are known for like just generating high amplitude waves. So perhaps you could have rogue waves, but probably not too common. All right. How do rogue waves form? My best guess is wave interference. So that's like if you add two waves together, right? So like if you have this point here, and then you have another wave, which is also at this point, they can add together and move up. And then similarly, if you have a trough here and you have another trough here, they can add together and move down. And so you have greater amplitude. And tsunamis are very large, not large in water. They only get high when they're close to shore. That is a very important fact, yes, and that is also true. The only reason why tsunamis are so tall is because the ocean floor forces them up. Normally, there might be tsunamis in the middle of the ocean, but because there's such a tall column of water because there's such a tall column of water, the crest usually doesn't like protrude much higher than the ocean level. But as the seafloor slowly forces the column to compress, then it also forces the top to go further and further up. And so that's why waves can get tall. The tsunamis are formed as earthquakes underwater. That is definitely one possible source of a tsunami. Volcanic eruptions could also cause them, I believe. What is the bottom of a wave called? The trough. All right. Formula of speed. I was talking about frequency earlier. Here's frequency. So v, the velocity, is equal to lambda, the wavelength, times f, the frequency. And it's also equal to lambda, the wavelength, divided by the time. Perhaps this is more common. If you've taken any basic physics class, you know that velocity is the displacement over time. And if we consider the wavelength as a displacement, then that fits the formula. Lambda f is a bit more confusing, but it's not too bad because we need to know that frequency is kind of the inverse of time. So recall that frequency is defined as the number of crests that pass through in 1 second. We can also, so then we have the units be some number over second. And so the units are 1 over second. And so the inverse of that would be just, we take one crest and see how long does it take to travel a wavelength? Annabelle, what is your question?
I can chat.
Hmm?
I can chat to you if you want.
Oh, it's fine. You can say it if there's anything else. Okay. I might be running a bit long. Maybe I'm taking too much time, so I'll hurry a bit more as we go on. Very important, very important, very important. Waves transport energy, not matter. This, if you've taken a physics class where you talked about waves, I'm rather sure your teacher would have mentioned this. It might seem like, oh my God, the water molecules that are moving closer and closer towards the shore. I mean, that's what happens with real life waves, right? When waves crash, they move towards the shore and then they recede. So intuitively you might think that water molecules are moving towards the shore, but that's not the case. That's just a phenomenon of waves known as breaking, which I will cover later. I guess, yeah, this is part 2 of waves. And just a fun fact, water molecules move in a circle in the ocean. So that means like their overall displacement would be 0, but they do move. It's just that they don't travel long distances. They all go back to where they started from. Wave-associated phenomena. This is a bit advanced, so probably I won't spend too much time on it. Fetch is the area where the wind constantly blows, and so this will create waves. A swell is a series of gravity waves which travel, and the surf is the area where waves break. Also lends its name to the sport. So as you can see, this is the fetch because the wind is blowing here, and then these are forming the waves. I should mention that wind is the former of most waves in the ocean. Do wind currents affect ocean currents? They're caused by the same things, but and I guess they could have some relation, but not too much. Can you go back a slide? Yes. So yeah. The swell was the area where surface gravity waves travel. So kind of that's kind of what we saw in the previous image where we had a lot of waves lining up. Yeah. And the surf is just here where the surfer is. Very cool. Next, okay, breaking waves. We got to here. So depending on the steepness of a beach, you might get 3 types of breakers. And so you have spilling breakers, plunging breakers, and surging breakers. And basically what happens when a wave break is, yes, they crash down. And that is due to the compression that I was talking about earlier of the water. So if you can see here, then if we are on this one, if we're looking at this one, then the median is basically the same. So there's not much reason for the water molecules at the top to want to go this way. So that's just a bit. But if we consider this one, like maybe this is the depth first, but then as we go up and up, then it's kind of forced out of the water. And so over here, gravity takes over and more of it falls over. Sorry for drawing poorly. Yeah. And surging breakers is just a very dramatic example of plunging breakers, where the wave basically just collapses upon going towards the shore. How much time do you have left? Coastal currents. Okay, so let me draw a coast, which is a very beautiful coast, and you will all agree. Boom, coast. So first type, longshore currents. So these currents hit the shore at an angle. So perhaps they're going this way, and then they kind of attack the beach from the side. And so what happens here is that stuff over here gets moved down here, and the longshore current may carry sand kind of along the shore. And so that's what happens with longshore currents. Rip currents, or rip tides, which are definitely not tides, you might have heard of as well. And these are just currents that move, why am I an eraser? That move away from the shore. And so this is why people always say, no, don't try to swim back shore in rip tide, because you're basically fighting against the wave. Perhaps it's more productive to try to escape the current by going to the sides, swimming parallel to the shore, and then, yeah. And then additionally, there's upwelling, which is basically when water from the bottom kind of does a flip turn up. So I guess if we look at a shore from this way, now like on this would be the ocean. So this is going to be the deep water, and then it's going to do a flip turn up. And this is important because cold water is more nutritious than warm water. And so this is what brings nutrients to the shore. Oceanic circulation. Okay. On the surface, they're driven by the Coriolis effect, which basically is just an effect that happens due to the Earth's rotation. So as you know, maybe you know by Newton's first law that things don't like to be moved. And so as the water, so if we have a water molecule that's over here and the Earth is rotating this way, then the water molecule, it appears to Earth, is moving this way. And so it will go that way. But then sometimes it might crash into a continent. And so it's forced up and then around kind of in this circular pattern due to Newton's first law. And so these are the 5 main gyres, or I guess the 5 main circles of, there's 5 main circles of that exist when it comes to circulation. And you should also know that along the west coast, the currents are generally narrower and quicker. All right, tides. Each tidal cycle repeats every 24 hours and 50 minutes. And so this is definitely a number that you need to know. You'll definitely get to at least one tide question per competition is my guess. And so yeah, tides, know your tides. There are 3 types of tides: diurnal, which is just one cycle in the 24-hour, 50 minutes; semi-diurnal, which is 2 high tides, 2 low tides in this time; and then mixed, which are 2 uneven high tides and 2 uneven low tides. And yeah, you should also, probably it's a good idea to know, if you live along the coast, which is like kind of like tide structure your coast falls into. Why 24 hours, 15 minutes? Probably has to do something with like the rotation of the revolution of the Earth adjusted for any movement along the path. And then also there's stuff with the moon going as well. Is this slide after ocean circulation? I think so. I don't know. What else is there? Yes, spring tides and neap tides. So 2 main factors cause tides. There's the sun and there's the moon. If they work together in a new moon or a full moon phase, then they pull water towards each other. And a neap tide, when they'll work against each other when they're at 90-degree angles. So these will be the first and third quarter. By the way, I was talking about a tide structure earlier. The Bay Area, or at least the California Western Coast, has mixed tides. So anyone who lives there, that's what we have. All right, ENSO, El Nino Southern Oscillation. Well, this is what causes El Nino, and this is kind of measured by the Oceanic Nino Index. This should be O and I. I don't know why I typed M. Yeah, under normal conditions, due to the Coriolis effect, water is going towards the west. But under El Nino conditions, ocean surface, first of all, this is the definition of El Nino, is when the ocean water heats up by more than 0.5 degrees Celsius for 6 months straight. And so when this happens, this turns this current on its head, and then the current starts to move in the opposite direction. And so instead of having upwelling here, we have downwelling here, and this is going to be bad for the fish living here. And when it's La Nina, then this current gets even stronger. So there are a bunch of effects El Nino and La Nina bring on rainfall throughout the world. I don't have time to cover it in this lecture, but feel free to search around and find what happens in your local area.
How does El Nino work?
El Nino is just the heating of the water causing currents to change. That's the one sentence explanation of what happens in El Nino.
But why does it do that?
Well, so under normal circumstances, the water is just moving in this direction, but when the water heats, there's some temperature imbalances, and then the Coriolis effect kind of gets canceled out by the winds that move this way. And so even though they're supposed to be moving in that direction, the winds actually carry them towards the shore on the surface. But underwater, there's nothing that winds can do. So the water will go back that way underwater. All right, tools used for oceanic research. There's a Nansen bottle, which is used to collect samples of water, and there's a dredge, which is used to collect sediment underwater. These two are really big ones. There are some other ones, but they're not as important. And finally, some tips and tricks. You have a lot of room to write everything down, so don't be concerned about saving space, but definitely be readable and know and be able to easily access information. That's my main tip for this event. Does global warming cause El Nino? No, but it can intensify, I believe. How does El Nino start? Just by the changes in water temperature. All right, let's quickly transition to the Kahoot. I will create one presently, and wait, I'm not gonna create it. I need to play a Kahoot. Start.
It's like 4:40.
Yeah. Sorry. I will be very quick with this. And let me also share the screen. All right, boom. You can share.
What was the last 3 slides?
I gave some tips and tricks. I talked about tools for oceanic research, and it was El Nino, I believe.
Can you share those slides and send it to the chat?
I will not share slides, but I will post the recording, and then you can pause at the slides to get the information.
I mean, like, can you like screenshot and then like send it to the Zoom chat?
I'm not very comfortable like sharing like the actual presentations out. But what I will do is during our break, I'll take any requests to go back to any slides. Does that sound okay? Whoever just spoke, I cannot hear you. Does anyone else want to join? All right, I'll start at 4:41. Oh, okay, we're getting botted. This is sad. All right, first question, which is the most abundant ion in seawater? There are two obviously wrong answers, and there's one that perhaps requires a bit of memorization of what I said earlier. All right, it's actually chlorine, not sodium. Chlorine is 55, sodium is around 35. I guess NaCl, it makes sense that they're most abundant because salt water, salt. Next. What is the difference between a seamat and a guyot? All right, good job, most of you. Okay, this is a very calculation-heavy question. Tsunamis are shallow water waves, so if you remember the formula for the speed of a shallow water wave, you can just plug the numbers in. Be careful of units. By the way, this question showed up in an actual competition. So this is what sometimes some of what you can expect to see. Lambda is the wavelength and F is the frequency, by the way. Okay, 13 is correct. The correct calculation is first you calculate the speed, which is the lambda times the frequency, that is 700 kilometers per hour. And then you divide the distance by the speed to get the time. So 10,000 over 750 is about 13.3. So it'll take 13 hours. Which of the currents is the fastest? So I will give you the general idea for this one because I kind of glossed over this during the lecture. So this is a question about Western intensification, which says the currents along the west coast of a gyre are faster. And you also need a bit of geography knowledge for this one. Okay, so Western intensification on the west side. So the Kuroshio coast is over here on the west, on the side of Japan. So that is definitely on the west side of the whole Pacific. The Canary is off the coast of Portugal. The Venezuela is also on the west side of Africa. And then, oh my God, it's a California current. It's California current, and it's on the coast of California. And so, yeah, Kuroshio current being the only Western current is the fastest. And by the way, I believe the Kuroshio current is the fastest current in the world. You might also want to take note of that. Mixed tides. Remember the time it takes for tides to repeat. And also be careful of AM PM. You do not want to miss points because of AM PM. All right, so the correct answer is 7:25 p.m. on the same day. For the people who chose red, you need to know that the tides rotate every 24 hours and 50 minutes. So the 50 minutes actually make a difference. People who chose green, you need to know that mixed tides alternate twice per day. So there are 2 high tides and 2 low tides within a 24-hour, 50-minute period. And so kind of the mix where these come is 7:25 p.m. on the same day. Which wave action caused drift of sand along the coast? So 2 of these are not wave actions. I guess they're more wave features. And so among the other 2, one of them causes the drift of sand along the coast. All right. So it seems like most of you were able to identify that rip currents and longshore currents were the ones able to cause action. But rip currents go out of the coast towards the open ocean. And so longshore currents are the ones that go along the coast. This is going to be a diagram, so I'm going to ask you to label F. Ooh, shoot, I did not talk about this class. Everyone give your best guess. There should be 2 that are obviously wrong, in my opinion. All right, yeah. Ooh, 4 of you got lucky, yay. This is a submarine canyon. Trenches would form normally further out here. Rift Valley would be much larger and also be parallel to the ocean floor. And I guess could be an argument that this is an underwater ravine, but I would assume ravines are also kind of like not on the shelf, and so just submarine canyons. Sorry, I'm not talking about this during class, so nice. All right, compared to pure water, seawater has, I'm not talking about pH. Okay, I should say the seawater has a pH of 8.1. So if you know what the pH of normal water is, it will be, you can find out what the pH is. Ooh, good job, most of you. Ooh, it seems more of you said it was higher pH. Yeah, the salt in the salt water makes water harder to freeze. So that would mean it would have a lower freezing point compared to pure water. 8.1 is higher than 7, which is the pH of pure water. So that's why it has higher pH. Next. All right, ENSO. Take a look at which direction the winds are blowing. And so you can find out which direction the current is blowing. And also take note of the heat maps. So orange would be hotter and blue would be cooler. And so because the middle of the ocean is hotter, that would mean we're in El Nino conditions. In normal conditions, there would not be this orange patch, and in La Nina conditions, this would be blue. And there's no fourth option for El Nino. Next. C4 spreading, which of the following does not result in C4 spreading?
Was,
I'll-
was tide after ocean circulation or no?
Perhaps there's not much ordering to my slides. They're just a bunch of information that are in the rules. So, okay. Seems like there are two you say. So A is a kind of a trap question. You would expect an increase in the rock age the further away because the rock comes from the middle and then it moves outside. So there'd be an increase in the rock age the further away the middle you are. Actually, there are a series of magnetic reversals. It's really fascinating. And that's actually how people were able to discover the existence of the Earth's magnetic field. But yeah. So results, fun. Let's take a break until 5 and yeah. Who wanted me to go back to the slides? Someone want me to go back to the slides or no? No? Annabelle? I have a request for tips and tricks. I also have no idea where that screen is.